Hi, class. Last week we looked at calculations that would be used if research compared differences between two independent groups. This week we're going to look at the calculations done when the research compares dependent groups, also known as paired groups. This is a natural two-point event, usually like a before or after study. And there's an inherent logical linkage between the data points. So in the example of a before and after study, each individual represents a paired data point, as each one has a before value and an after value. They are paired, and this is one more piece of information that we know so the test can be more powerful. We could use the independent t-test from last week, but the ones presented here give us more detail. With these tests, we don't have to worry about the standard deviation because the participant essentially won't be changing. For example, a person's biological sex doesn't change during the course of the study. Age will change, but all the participants in the study will age the same amount, so that won't affect our variable of interest. We still have a dichotomous variable, but this time it's split by the two sides of the paired group. If we continue with our before and after example, the before the treatment and the after the treatment represent the two possibilities for the variable. We have similar assumptions to the ones that we discussed last week. For the parametric test, we assume a normal distribution of data, measuring the dependent variable at the interval or ratio level, similar variance, and random sampling from the population. The observations themselves, so not the groups, are independent as they were last week. We also assume that the difference between the two scores for each participant will be normally distributed. However, for sample sizes over 30, violating this assumption is not likely going to cause problems. For the non-parametric test, we assume random, random sampling and independent observations also. The parametric test is the paired samples t-test, which is also known as the repeated measures t-test. Again, we have one group of people and we will collect data from them on two different occasions or under two different conditions. Let's use the example research question that looks to find out if there is a significant change in the participants' fear of statistics test scores following their participation in an intervention designed to increase their confidence in their ability to successfully complete a statistics course. And we want to know, does this intervention have an impact on the participant scores on what is called the fear of statistics test? The participants are going to take this test before and after the intervention. Here, you've got one set of participants and two variables. One categorical independent variable, time 1 and time 2, or before and after, and one continuous dependent variable, which is the score on this fear of statistics test that's measured on two different occasions. The test is going to tell us if there's a statistically significant difference in the mean scores for time 1 and time 2. So let's start by looking at SPSS. And of course, it always takes me a minute to click all the right buttons here to share my screen with you guys. Let's go ahead and share the entire screen and allow it. And let me quickly just bring this up. So you should be able to see this now. So we open up our data file, data set in SPSS, and then at the top of the screen, we're going to click Analyze, and then Compare Means, and then Paired Samples t-test. We're going to choose the two variables that we want to compare. So in this case, they are the fear of stats time 1, which is right here. And you can even see it if you hold it up. It's FOST1, okay? And we're going to move that into the paired variable. And then we've got fear of stats time 2. Move it over there, okay? And then we click OK, and we look at the output. Now, in the table paired samples statistics, sorry, wrong one, paired samples test, you look at the last column called sig two-tailed. Here you go. This is your p-value. If it's less than 0.05, you can conclude there's a significant difference between your scores. Here, the p-value is 0.000, although the table rounds to 3 places. So the actual value was less than 0.0005, which is substantially smaller than our specified alpha value of 0.05. So we can conclude there's a statistically significant difference between time 1 and time 2. We note the t-value of 5.39 and the degrees of freedom, 29, which we will report in our presentation. We also note the mean difference of 2.667 with a 95% confidence interval that stretches from the lower bound of 1.655 to the upper bound of 3.678. Now that we know the difference is significant, we need to find out which set is higher. So we look at the output box called paired sample statistics up here to find the mean scores for each set. Here, time 1 mean was 40.17 and time 2 was 37.5. So we can conclude that there was a statistically significant decrease in test scores from time 1, again, which was before the intervention, to time 2 after it. Now remember, even though we can show a difference in the scores, we can't prove that the interventions caused the decrease. There's many other factors that could have impacted the scores, and these are called confounding or contaminating factors. Good researchers do all they can to anticipate and control for these or incorporate them into the research design. Now, even though we've determined that the difference was unlikely to occur by chance, we still don't know much about the magnitude of the difference. One way to do this is to calculate an effect size. SPSS doesn't give us this in the output, but there are websites that can help you do this. One helpful one is www.cognitiveflexibility.org/effect size. When you read research done by others, you might run into either Cohen's d or eta squared effect size. For Cohen's d, 0.2 is a small effect, 0.5 is a medium, and 0.8 is a large effect. And for eta squared, 0.01 would be a small effect, 0.06 is moderate, and 0.14 is a large effect. So in our case, eta squared is calculated as t squared divided by the sum of t squared plus n minus 1. I know it's kind of hard to follow, but what we would look at, again, our t value is 5.394 squared divided by 5.39 squared plus 29. So remember, we have n is 30 minus 1 is 29. Okay? When you do this math, it ends up being 0.5, and we can conclude that there was a large effect with a substantial difference in the test scores gathered before and after the intervention. Now, if you reported this, it would look this way. Let me find this slide for you that I made up. There we go. It would look like this, or if you read it in a journal article. Okay, paired samples t-test was conducted to evaluate the impact of the intervention on students' scores on the Fear of Statistics test. There was a statistically significant decrease in FOST scores from time 1 to time 2. And it's got the mean and standard deviation in there, as you can see. And it even says the mean decrease was 2.67 with a 95% confidence interval, and it gives you those boundaries. And then it reports the eta squared statistic and says that it's a large effect size. Now, let's get back to this, our data set, okay? Because the non-parametric test is called the Wilcoxon signed rank test, sometimes referred to as the Wilcoxon matched pairs signed rank test. Instead of comparing the means used in the repeated measures t-test, this one converts scores to ranks and compares them at time 1 and time 2. So let's walk through the steps to do this again, okay? We're going to get back into SPS. We're going to start with Analyze, okay? Then we go to Non-Parametric Tests, and we're going to pick Legacy Dialogues and 2 related samples, okay? Again, you're going to choose the variables time 1 and time 2. So Fear of Stats time 1, Fear of Stats time 2, and move them into the test pairs box. Then we've got Wilcoxon clicked in the test type. And under options, we're going to pick quartiles, okay? Then you click continue, and you click OK, and here's what your output looks like. Now, we first want to look at the Z value and the associated significance level. So let's get down here, which you can see sig, okay, two-tailed, that little box, okay? If the significance level is equal to or less than 0.05, you can conclude that the difference between the scores is statistically significant. Here again, we have 0.000, which is rounded from less than 0.0005. So the scores are statistically significantly different. The effect size can be calculated using the same procedure we did last week for the Mann-Whitney U. We divide the z value by the square root of n, and you can ignore any negative sign in front of the z value. And remember, n is the number of observations of the 2 time points, not the number of cases. So for this example, z is 4.18, n is 60, because remember, right, we double 30, okay? And when we do that math, we see that it's 0.54, meaning a large effect, okay? Now, results are going to look like this. Let me get this other slide for you. Okay, if you saw it in a journal, it would look like this. A Wilcoxon signed rank test revealed a statistically significant reduction in fear of statistics following participation in the training program. Well, it looks like I got a little typo there. The median score on the fear of statistics scale decreased from the pre-program median to the post-program median. Now, we'll work through an example of these during our Collaborate session. And now that we've covered studies that compare 2 groups, we're going to be moving into studies that compare more than 2 groups and the analysis of variance. All right, let me get back to my screen. And oops, there we go. Sorry about that. And we will stop sharing so you don't have to look at that anymore. And have a great rest of your day.